This is Surveying 1, Lecture 6, and in this lecture we will continue with the topic of distance corrections. And again, this is mostly having to do with taping corrections, but some of these concepts will be applicable to distance corrections in general and really to surveying measurement corrections as well. So let me talk about the first two slides I had in the previous lecture. Just wanted to review again that our basic equation for distances is that the corrected distance is equal to the measured distance plus corrections, the sum of the corrections. And that the generic form of this is that the true value is equal to the observed value plus the sum of the corrections, understanding that the corrections themselves may have a positive or a negative sign. So now let's talk about tension, and I'm not talking about all the tension you're feeling because we're getting into some stuff that may not be that understandable and you're feeling the tension of having to know about this on the next exam. Tension in this case has to do with the fact that when you tape, you have a tape that's not moving. And it's not moving because you're applying equal amounts of tension at each end. If you're not applying tension, then you're not taping correctly because that means the tape has some slack in it, and that's one of the worst ways of measuring because you're going to have error no matter what. So what happens is steel is an elastic material up to a certain point. So the harder you pull on this thin ribbon of steel, the more it's going to stretch. And what this is a discussion of the fact that pulling on the tape does cause it to stretch. So there is an equation that can be used to calculate how much that stretch is, but the easy out is that you try to match the calibration tension so that it zeroes out. As you'll see from the equation, that's very clear. So C sub P, and just because we've used T for temperature already, we can't use T for tension, so we use P for pull, is equal to P minus P sub S over AE, and all of that times the distance L. P is the tension used in the field in pounds. P sub S is the tension used in calibration, also in pounds. L is the total length measured. A is the cross-sectional area of the tape. So the tape, as you know, extends out this way, but it actually has a cross-section. And so there's a fairly easy way to calculate it by knowing the density of steel and the length of the tape, and calculating the total volume of the tape and dividing it into the density. So a cross-sectional area of the tape, it's usually a few thousandths of a square inch. And then E is what's called the modulus of elasticity of steel, and that's in pounds per square inch. And the number we typically use is 29 million, 29 times 10 to the 6th. Hopefully you understand scientific notation. So this is the equation that we would use if the tension we use in the field is different from the standard tension. Now this is not something that we will particularly do in our classes frequently, but it is an exercise where we will have you use different amounts of tension so you get an appreciation for what it is to be able to tape accurately. So simple problem, 500 feet is measured with a pull of 30 pounds, P sub S is 15 pounds, cross-sectional area of the tape is 4 thousandths of a square inch. So C sub P is equal to the pull we used in the field, which is 30, minus the standard tension divided by AE, so 0.004 times 29 times 10 to the 6th, and of course all of this times the 500 feet. So plugging it into the equation is fairly straightforward, and we do 30 minus 15, divided by 0.004. Divided also by 29 million. And on this calculator, you enter that as 29, hit the EEX button and then the 6, so you see 29 times 10 to the 6th is what this is supposedly saying. So you divide by that, and then we multiply by 500, and we get 0.0647. So I'm going to call it 0.065. And now that we're done with all the calculations, I can round it now to 0.07 and add that to the 500, because in this case we have some pull. So the answer would be 500.07. The next thing I want to talk about is sag. So when you have a tape that's used in the field and it's end supported, so using a plumb bob at each end, you have a certain amount of sag in the tape. And that sag tends to pull the two ends of the tape together, so they're never exactly 100 feet apart. One way to eliminate the sag is to use what's called normal tension. And normal tension is a very specific term. It's not the tension used to standardize the tape. It's the tension where the stretch of the tape from the previous discussion, the pull on the tape, the tension can cause the tape to stretch, cancels out or equals the shortening effect due to sag. And so we have an equation for calculating what this is, and again, this is not something that you want to use if you can figure out what normal tension is. This way you simply can ignore C sub P and C sub S. So C sub S is the weight per foot of tape. So you typically would weigh the entire tape on its reel, then you take the tape off the reel and just weigh the reel so you know the weight of the tape, divide that by 100 to get the weight per foot of tape. So it's the weight per foot of tape squared times L, which is, I've written it intentionally as a script L, and that number cubed, that's the length of a single end supported span of tape. So that could be the full 100 feet, that could be 50 feet or 65.73 or whatever. P is the actual tension you used in the field. And note that this L, I just pointed it out already, is very different from the previous concept of L, where L is the total distance. So capital L is always the total distance. Script L is often used to indicate the span of tape that's used. So 100 feet are measured, end supported with a tension of 15 pounds. The full tape weighs 2 pounds. What is the correct distance? So substituting into this equation, W squared L cubed. So in this case, W, little w, is 0.02. So it'd be 0.02 squared L cubed, so 100 cubed over 24p squared. And the tension is 15 pounds, so that would be 15 squared is 225. And that number works out to be 0.074. And the reason I didn't use the 500 or some other number here is to point out how serious the impact of sag is. Probably when you start doing your labs, you will be using 15 pounds tension, because for most people 30 pounds tension is really hard to handle. But typically normal tension is even higher than 30 pounds. It could be 40 pounds, and it's really hard without practice to actually get there. And so one of the ways to overcome that is to use different values and then calculate the effects of sag. You see though, with just 15 pounds tension on a typical tape that weighs 2 pounds, it's 7/100ths of a foot. That's getting very close to a full inch of shortening for every 100 feet. So this is something that you should be very aware of, because surveyors typically say, well, I just pull hard. Well, what is pull hard? Do you have a calibrated arm? How do you know what the correct amount of tension is? Because you cannot look at the tape and tell when the shortening effect of sag has been removed by pulling hard enough on the tape to stretch the tape. And by the way, this varies. A light tape will be much easier to stretch. A heavy tape will be much harder to stretch. Now, I worked out this same equation, but for a 50-foot span. So in this case, L is equal to 50, okay? So the W would still be the 0.02. So we have 0.02 squared times 50 cubed this time. The denominator is the same, so 24 times 15 squared, which is 225. But look at that. In 50 feet, the shortening effect of sag is just a tad under 100th of a foot. Okay, so it's a really important thing to understand that on short spans, yes, you can get away with not worrying too much about sag. But on a full 100-foot span, it's important. And again, you need to know the weight of your tape, because if you have a heavy tape, that can be a real problem. Now, let's talk about combining corrections. When there is more than one correction, so you might have a calibration, so incorrect length, you might have temperature and so forth, slope, you calculate each one as if the tape is nominally 100-foot length. For very long or very steep lines, the order in which they are to be applied may matter depending on the desired accuracy of the result. And the most common thing is to first apply the correction for slope and then just combine all the others together into one measurement. So let's talk about some common taping mistakes that can occur both with experienced people as well as inexperienced people. The issue with experienced people is that they tend to be lazy and not use the tape, and yet there are times when you are forced to use the tape for whatever reason. Sometimes it's actual physical conditions where you simply cannot sight at the target, or you forgot and left the prism at home, and there's all kinds of reasons why you sometimes have to resort to using a tape. And one of the most common things that happen is not using care in trying to decide what the problem is. In other words, remember that general equation is true equals observed or measured or indicated plus the correction. And so are you solving for the true, or are you solving for what to measure out? And that's the first area that people have a lot of trouble with. And this is something you can have trouble with EDM and other kinds of technologies as well. Now here's some common taping mistakes. So now we're not talking about errors, but blunders. One of the most common blunders is you're on the wrong side of the tape and you decide to be smart and read that number upside down because you know you can read numbers upside down. And numbers like 6 and 9 can be confusing. And so what I tell people is to follow a certain procedure, which is whenever you read off a number, before you call it out, and you should always call it out, look at the two adjoining graduations and see if they are in the sequence that they should be. And it's not just upside down. Sometimes the numbers are unclear. Sometimes the numbers are simply worn, or the tape could be dirty or working in muddy conditions or whatever conditions that causes dirt to accumulate on the tape, or it could be snowy or icy and you get lazy, your fingers are freezing. Wind is blowing hard, it's easy to start taking shortcuts. So always look at the adjacent numbers to verify that what you are deciding is the value is the value. Another common mistake is simply writing down the wrong number in the field book. So the typical procedure that I recommend you follow, and everybody really recommends, it's not just mine, is the head tape person will say whatever they're reading for a fraction of a foot, like 0.65. The rear person will say 100 or 50 or whatever. Then you decide who it is, somebody calls it out, 50.65. Then the note keeper, if it's a third person, will call out 50.65 and write it down. If it's not, if it's one of the tape people who write it down, they write it down, then read the number back out, 50.65, so that the other person who should be paying attention will say, nope, that's not what we agreed, or yes, that's correct, and you go on. Another common taping mistake is to lose track of tape lengths or other partial measurements. You got a long line you're taping and you lose track of the measurements, you don't count your chaining pins. You may have noticed there are 11 chaining pins on the ring. That's so you can go 1,000 feet at a time. Chances are most people will not go 1,000 feet, but sometimes you have to, for various reasons, not measure a full 100 feet more than once in the measurement. Because the ground is rough, you got shrubs and bushes and undergrowth and all kinds of things to work around. And you lose track of tape length. So what you do in a situation like that is you actually write down every single tape length or partial tape length. Then you make mistakes with the ends of the tape. You don't go out with the correct end. You should always go out with the head tape person holding the zero end. And you get that confused and you start making mistakes. And so what that usually leads to is reading the fractional foot, the tenths and the hundredths, incorrectly. And in that case, yelling out the number till the cows come home isn't going to help you because you'll still be calling out the incorrect numbers. Now let's talk about some of the other errors. These are not mistakes, these are errors that can happen. So when you tape, so this is looking in plan view. Now, if you've forgotten, plan view means we're looking down from above. We start over here and we wish to tape along this line. But when we lay the tape out, because we were lazy and didn't put some kind of a marker, like my pen is the range pole sitting right there, so that the rear tape person can look at where the front end of the tape is, you get lazy and you don't do anything about that to make sure the tape is actually on the line it's supposed to be. If the tape is out of line by 1.41 feet, the square root of 2 basically, that will cause this mark on the tape on the ground that you place at the 100-foot end to be 1/100th of a foot shorter than 100 feet. So you automatically get 1/100th of a foot error shortening. It's always shortening, it's never lengthening, okay? And one of the things that you might want to do is calculate what is it if it's 2 feet and 3 feet and so forth. So that's one kind of an error. Keep in mind that if you look at it in elevation view or profile view, the side view, it's the same deal. So if you are looking at this and one end of the tape is lower than the other end by 1.4 feet, you also have 1/100th of a foot error. And that's why I recommend that people make sure that the ends of the tape, both horizontally and vertically, are in alignment by about 6 inches. That way you can be very comfortable to know that you're keeping your errors very well controlled due to alignment in the horizontal plane as well as in the vertical plane. Now here's something else that people don't think about too much when they're new at this, and that is if you have a line that's going to be measured, again looking at this in plan view, and you verify that the front end of the tape is actually on line when you make the measurement, but you don't snap the tape, and you have to be very careful doing this so you don't break the tape, physically break the tape, but it turns out the tape is actually laying on the line like this, where the middle of the tape is 7/10 of a foot, okay, out of line, about 8 or 9 inches. Well, that will also create 1/100th of a foot. And you can actually do this calculation to see how that works out. In fact, this problem, looking at it in elevation view now, when you have sag, that's in effect what's going on, except in sag, it's not a nice straight line, it's an actual catenary curve, so it's a bit more complicated of an equation to calculate. So keep in mind that this applies with horizontal and vertical alignment, and they're additive in the sense that you never make a compensating error that's in the other direction to get back the shortening effect of being out of alignment. Now there's various kinds of random errors in taping, and the most common of them have to do with marking the points. So when you are measuring end supported, you got these plumb bobs, they're swinging around and so forth, especially when you're first trying to do this. Sometimes you'll catch the plumb bob when it's on the forward end of its swing or the back end of its swing, assuming you're going that way. And so you sometimes mark the ground either a little bit ahead or a little bit back of where the true vertical is. The same thing happens at the other end. So one of the things that we understand from random errors in taping is that those plumbing errors tend to be, now not the error due to sag that shortens the tape, but the actual plumbing errors will cause errors that are variable in sign, meaning they can be plus or they can be minus, and of course variable in magnitude. And we'll talk about this more when we talk about analysis of random errors a little bit down the line. Similarly, simply marking the tape even when you're laying the tape out fully supported on the ground, when you place that chaining pin in the ground, or when you place the 100 end on that first mark, how well are you aligning those points? There's always some variation. There's a human inability to line things up perfectly. Yes, we can get very close, but sometimes we're a little bit ahead, sometimes we're a little bit behind. So that also creates variable random errors that are variable in sign as well as magnitude. The good thing is that most of these random errors tend to cancel out. They still accumulate, but they tend to cancel out a little bit, unlike the systematic errors such as the alignment problem, which just keeps reducing and reducing and reducing the accuracy of the result, because every time you make another measurement, if you keep being out of alignment, then you're making your difference between the true value and your measured value larger and larger and larger. So alignment errors, do they cancel out? That's a question that you need to think about. I've just talked about it, but think about it. Tape horizontal errors. So if the tape is not horizontal, do they cancel out? Tape that's incorrect length, let's say the tape is too long or the tape is too short, that doesn't cancel out. It always accumulates. Temperature variations, this is an interesting one, because if you are measuring during the course of a day and you have temperatures that go up, then they go back down, and it's all the same line, keep in mind it has to be the same line, it could be they cancel out. But that's not a really good excuse. You can't count on that. The other thing that can happen is on the same line, part of the measurement is in shade, part of it is in the sun, there's variations in temperature, the wind picks up, the temperature changes during the day, you have clouds that show up, you're in the woods, all these kinds of things can cause variations. So you can have systematic errors that show up due to temperature that can cancel out. but mostly they're additive, or to make sure you understand, I've also thrown the word subtractive, meaning they can all be positive or they can all be negative. Sag errors always accumulate and they're always subtractive, meaning you tend to get true distances that are less than the actual indicated value. And as I said, one way to overcome this is with normal tension, so that the pull, the stretching effect of the tape is canceling out the shortening effect of the sag. Now, we won't go through this as an equation, but this is the equation for calculating what's called normal tension. And here, W is the weight of the entire tape. So if the tape is 100 feet, it'll be so many pounds, like 2 pounds. You know what A and E are already. Now, the interesting thing is normal tension is on both sides of the equation. So this is an iterative procedure usually. What you do is you solve it using a certain number, using the values you do have, and you try it again and again and again until you get it to match up. So the thing that you might want to think about when you're taping is this list. A lot of textbooks will list a longer one, but I've taken the most important ones, or the ones that you need to think about most. So what causes error of 1/100th of a foot in a 100-foot measurement? Well, first of all, it could be a 0.01 foot error in calibration, meaning you didn't calibrate the tape and the tape is actually longer or shorter by 1/100th of a foot. It's not usual for a tape to be off by more than 1/100th of a foot, but it can happen. In fact, I had a tape that was a whole foot off. Tape like that really shouldn't be used. A 15-degree Fahrenheit, this is Fahrenheit, I should probably have thrown that in, so let me just put that here in parentheses. A 15-degree Fahrenheit change in temperature, either upward or downward, will cause the tape to either lengthen or shorten by 1/100th of a foot. Most of the time, for most average tapes, about a 15-pound tension will cause 1/100th of a foot of variation. Sag, I did it a little bit differently. If you have about 6/10ths of a foot of sag, meaning the middle of the tape is below the line by about 6/10ths of a foot. Remember, we talked about the alignment problem. So here we are looking at it a little bit differently. It's a way to look at the tape and try to judge about how much shortening impact you have. And then you notice that the last one here, 0.7 foot error, is a 0.7 foot error in alignment at the middle of the tape, or in level at the middle of the tape, will also cause a 1/100th of a foot measurement. It's slightly different because the shape of the tape is different. Here we're assuming a right triangle going from the end point of the tape to the middle where it's 7/10ths of a foot out, and then another right triangle going back to the other end of the tape. And then, of course, 1.4 foot error in alignment or in level between the two ends of the tape, where the tape is truly straight between those two endpoints. So, good taping technique. One of the things I tell people, whether they're new at this or not, and this is true even for things like GPS and electronic distance measurement, always try to know what the distance is so that you can catch mistakes and blunders, not only that you make or your team makes, but sometimes instrumentation will deliver an incorrect result. There's tons of stories once you start talking to experienced surveyors where they will tell you that with technology where you're not directly measuring like you do with the steel tape, you can often get incorrect results, but you bank on it because you paid so much money for it. And so I always say try to learn as you survey more and more to estimate distances by eye. The other is if you're taping, or even if you're using a distance meter and it's close by, pace it off. That's one of the reasons for calibrating your pace. and then compare with what is actually measured. One of my favorite sayings is to always tell people, know what the answer is before you actually do it. Now, you don't really know, but you have a pretty good idea what the answer should be so that you can catch those kinds of things. I've already mentioned this. Always look at adjacent footmarks. Always double check each individual 100-foot or sub 100-foot measurement. What do I mean by this? So here you are, you're using the tape, end supported or fully supported. You stretch the tape. If you're the rear tape man, you're making sure that you have 100 on the mark and the front person is reading off tenths and hundredths of a foot. If you're measuring a sub 100 foot, if you're the rear tape man, you're holding it, let's say, on 57 exactly, and the front person is reading off the fractions of a foot. Once you do that, so you say 57.63 or whatever, then relax tension, look at each other, then go back and repeat the measurement one more time. Doesn't take very long to do that again, but it's a great way to make sure that you haven't committed any blunders. That's what I mean by double checking in this case. This is what double checking in this case means. Something else that is sometimes helpful is to make sure that the zero end is always going downhill if you're only going to measure the line once. You'll have to think about this, and with experience you'll understand why this is true. The other thing to do is always tape a line twice. So always measure it from one end to the other and then from the other to the beginning. We talk about doing this with all the other technologies as well, with its EDM and GPS and so forth. And finally, with taping, your stance and your grip should be stable. So what do I mean by that? I've already talked about this a little bit, but if you are taping, or if I am taping, I should only be facing, or I should only appear this way to you, is if you are standing normal to the direction that I'm taping. So if I'm taping this way, and I'm a right-hander, then this is the way I should be standing, with my feet apart, where my feet essentially are in a line that's parallel to the direction I'm taping. And this way you are able to use your arm and have a good grip on the tape, whether you're using a tension handle, whether you're using your fingers, as I demonstrated in one of my lectures, or using a clamp. If I was measuring that way, I'd be using my left hand. I'm not very comfortable using my left hand. So the only way I could do this measurement is if I actually turned around so that I could use my right hand to hold the tape. The left hand for a right-hander would be the hand that holds the plumb bob if you're using a plumb bob. Obviously, if you're a left-hander, you'd switch all those things around. Finally, just want to talk a little bit about precision. I will be asking you in your labs to calculate precision because I'll be asking you to make all these measurements more than once. And this varies a lot, so don't take this to the bank, but for high-value properties, it's often considered reasonable to tape to a precision of 1 in 10,000. In rural work, you tape with average taping quality, and that would be about 1 in 5,000. But it depends on conditions. You could have situations where you need more than 1 in 10,000 in the city or less, and similarly for rural work. If you get consistent value, if you're a surveyor and you're a professional surveyor and are consistently with taping, getting 1 in 2,500 or less, it's considered poor. Now, most students will have a hard time getting to that on their first few attempts, and that's okay. This is a process of learning. I'll tell you right now, for those of you who have some experience with surveying, you think you do far better than this, but I will soon disabuse you of that notion. And finally, just wanted to point out that while these are considered the ranges of taping precision, the geodesists, people who measure the shape of the earth, need precision much higher than that. And 1 in 100,000 is not uncommon. And this was done even long before the days when steel tapes were available. Now the chains that the GLO surveyors used to measure weren't good enough, so they actually used bars that were of certain length that they would place end to end to make those kinds of measurements. So there were measurements done, distance measurements done in the 1800s and even the 1700s that were easily of a precision of 1 in 100,000 or better. And in fact, those were some of the first measurements that were done to determine the size of the Earth, the diameter of the Earth, the length of an arc of latitude, and so forth. And with that, we will bring this lecture to a close.